Bump bump. Hey guys, what's going on? Memes here. So, you ever notice something while perusing the internet for kind of something I came across different things. And apparently I learned from Thad that Professor Einstein, when asked how he would solve a problem within an hour, he said he would think about the problem for about 50 minutes and come up with a solution and implement it. So asking questions, the right questions, is important. Is this the right question? I don't know. What is the simplest universe? All I know is from at least my algorithm. Oh, the first videos are from Thad and Event Horizon on YouTube, where I consume a good deal of content. The other question I had is, what's the simplest Turing machine? Because I hear a lot of people going on about it within the realm of computation. Professor Wolfram, specifically, and it basically offered a prize, and I guess a student won it in about 6 months. Now, the reason why I say this is because I got to thinking. I was reading Thad's book. I didn't link it, but you can find it on his channel and stuff. As we can see here, we have Professor Stephen Wolfram. And again, to be fair, this prize was awarded by Wolfram Research. Has it necessarily been fully proven? Does it totally hold up to the definition of a Turing machine? What is a Turing machine? A Turing machine is a mathematical model of computation describing an abstract machine that manipulates symbols on a strip of tape according to a table of rules. Despite the model's simplicity, it is capable of implementing any computer algorithm. It's basically what it's called if it's Turing complete, to my understanding. Now, what is the whole point of this? Well, all I'm saying is I've been very privileged to come across a lot of different really cool and really smart people on this internet. And one of the videos I was recommended to share to people first coming across Thad's model.
Let's build the simplest possible universe. Okay. Just geometrically. We're going to start like that. We're not going to be so concerned about building our universe at first.
I'm pretty sure, according to Jonathan, is if we have a proper label on the can of soup, that's a cylinder. And a cylinder can be deformed into a sphere. And that's very important within physics. I'm just saying.
Because the general concern of how would you build any universe, it gives you a little more intellectual leverage to try that starting process, right? And basically, step one is the one everyone's been stuck at here. So to make step one easier, let's say we want to just describe the simplest possible universe. By possible, we literally mean self-balanced. So we
is it just me, or does that kind of sound like the principle of least action, if you're going for simplicity?
I mean, there's no continual system, exterior system injecting into this to keep it going. There's no boundary conditions that some God needs to put in place or some other entity, right? It's a system.
So, does that sound like a Cardano machine? Because apparently you can't necessarily create energy, but you can keep on trucking. That is my understanding of it. Hi, Laura. Good to see you. But we continue.
System that maintains itself, that defines its own self-balanced.
The long story of this is essentially you can basically parameterize the realm of our persistence using time, space, mass, charge, and temperature. Go into Wolfram Alpha, play around with whatever you want, and apparently you can break it down to those 5 things are there or some combination thereof. Okay. Now, again, what does this have to do? We're going to go back to Professor Wolfram's vlog over here. All right. We go to the thing. Here we go. The prize is won. Now, this is the fascinating part. We're getting to what I found. Okay. Here it is. Looks a little bit like Rule 30, but a bit different. Just 2 states and 3 colors, able to do any computation that can be done, given enough time. Oh, look at that beautifulness. It's doing all different types of stuff and things. Okay. Get this action, this, 2 states, 3 things, and depending on how you set it up, it can do very novel computation. it was theorized you could do the 2-3. And again, isn't necessarily fully official. No, this is according to Wolfram Research. It's technology that runs Alexa and Siri. Just saying. So as we can see, there were simple Turing machines, the record being a 7-state, 4-color machine from 1962. The record stood for 40 years till 2002. It gave a 2-5 universal machine in a new kind of science. Oh, well, thank you, Professor Wolfram. We know that no 2-2 machine can be universal, so the simplest possibility is 2-3. And from searching the 2,985,984 possible 2-3 machines, I found a candidate. Sounds like a very Professor Wolfram thing to do. He also found like a proof for Boolean algebra that a lot of people really, no human being apparently understands, according to him. I found a candidate which, as of today, we know actually is universal, Professor Wolfram claims. From our everyday experience with computers, this seems pretty surprising. After all, we're used to computers whose CPUs have been carefully engineered with millions of gates. It seems bizarre that we should be able to achieve universal computation with a machine as simple as the one above, that we can find it by just doing a little research in the space of possible machines. To be fair, I have been a bit skeptical. I understand there's a lot of power. We can model a lot of things. My skepticism is quickly disappearing about the computational universe. Like, I know there's power, but we're getting to it. We're getting to it. Okay. So, where is it? All right. Is it true? The fundamental principles of science, Turing machines. Okay, we're going to get to the point where, all right, they announced the prize on June 30th, just 47 days after they announced. All right. It hadn't quite proven it, so basically, some refine. That sounds a little bit like peer review. I'm just saying. So basically, it doesn't halt. And Alex Smith's construction of the Turing machine tape memory must be filled with an infinite pattern of bits. But the key point, the pattern bits can be set up without doing universal computation. So that means that we see universal. So that means that when we see universal computation, it's really being done by the 2-3 machine, not somehow by the encoding we're using. Okay. Where is it? It was serious. I apologize. All right. Haven't quite proven it. Basically, long story short, is the Turing machine must involve only a finite number of non-zero bits, and the Turing machine must halt. The 2-3 Turing machine doesn't halt. Basically, the construction, the Turing machine tape must be filled. Basically, he ends up setting up a parameterization. The machine restarts, and then it's capable of universal computation. And Wolfram Research essentially claims that it's a way to actually do universal computation. All right. That's wonderful. What the heck does this have to do with the universe? All right. We go back to Thad's guided reading of 44. This is the absolutely fascinating thing, because if it's true, and this actually parameterizes quantum field theory, and GR emerges using a constant set of units, here we go. This is what I noticed.
It defines the second simplest geometric form, the minimal hypersurface known as the Clifford torus. Here we are diagramming the projective tangent cone of the Clifford torus, the familiar conic division boundary of projective hyperbolic geometry.
The donut
tangent
theory
cone of the
thingy.
Clifford torus defines the projective null cone of hyperbolic geometry. The entire surface of this hypercone defines the division singularity of the external domain. And the balance maintained by this constructive arrangement between the future hypercone and the past hypercone defines the hyperplane of the present, the most trivial minimal hypersurface. As a helicoidal product surface, the Clifford torus defines the simplest and most symmetric flat embedding of a Cartesian product of two circles. That is, it defines the...
Okay, so essentially this whole thing is, you go back here, these are basically, you'll see the space-time diagrams. Sir Roger Penrose, Professor Penrose uses them a bunch. Basically, all right, there's the past, there's that. We can only see out to like 90 degrees apparently within whatever vector we're moving in. Okay, we go back here. And the thing about the asymmetric Clifford torus being, but one of the circles is really big, one of the circles is really small, is you can actually embed it in R2. So you get R2A, R2B. So basically, I'm pretty sure you can. That allows you to do the disk thing. I believe it was Professor or Dr. Kaufman that was speaking to Professor Wolfram was mentioning, because a trefoil will not bound a disk. Sounds like you can do two disks. I think it might lead to a double cover, if you will, perhaps a double cover lattice. Continue, Thad.
Product surface. The Clifford torus defines the simplest and most symmetric flat embedding of a Cartesian product of two circles. That is, it defines the simplest connection between two circles, each of which possess their own independent embedding space, resulting in a product space that's R4, the four-dimensional hyperbolic spacetime of general relativity. But that's not the end of the story. Since this helicoidal surface connects two circles of significantly different size, the chiral connection of its rotation operator is highly asymmetric, causing the Cartesian product of these two circles to twist into an R3 torus. Under asymmetric chiral connection, this is unavoidable.
All right. So what I'm hearing here is, again, if that stuff is true, and it's looking more and more like I think he's got it. I think he's got it. That just kind of sounds to me that once you have the parameters of our existence, it's just going to naturally, it needs to twist into an R3 torus, which, as far as I understand it, is apparently how we observe the universe. I'm just saying, let's do a little more.
First circle in that connection consumes x and y, leaving only one independent axis, z, available to the second circle. This quickly collapses the R4 domain into an R3 projection. That is, a torus embedded in R3 is an asymmetric reduced dimension projection of the maximally symmetric Clifford torus embedded in R4. The generalized equation for the tangent cone of the...
All right, we're getting a little bit more technical there. Again, this is available. The links in the doobly-doo and everything. If you want to pick up a copy of Thad's book, totally cool. But I'm just saying that I'm just watching. I'm like, okay, this Turing machine restarts. It sets up the parameters, and then it does its thing. And that's capable of universal computation. Turing complete, if you would. And if the parameters of our existence, our realm, you may say, are parameterized, and some may say going from R4 to R3, is that a reset? I don't know. We're operating in a different dimension. I'm just saying that I think it's kind of cool. And I also see a 2 and a 3, so it kind of seems like 5. So depending on how it is, I don't know. All I know is peace out, everybody. Be safe. Hopefully this was useful for somebody, because, well, they could use some of that right now and in the temporal future. Peace out, everybody. See ya.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.